It's not really a talk on automorphic forms per se. It's about something which just sounds very elementary and actually is. And probably you're not going to believe that anything new could be said about this. And it's possible that you're right, but I guess we'll find out. So what am I talking about? So let's start off with let K be a field, any field actually. And as you know, if you take the polynomial ring over K, this has a lot of properties in common with the integers. It's because it's a Euclidean domain with respect to degree of polynomial. So it's got a division algorithm. It's got unique factorization into primes, and the primes are the monic irreducible polynomials. So, you can do arithmetic. Now, historically, when people think about it this way, they usually assume K is a finite field. And I'm not going to in this talk do that. I'm going to be thinking of K as being an infinite field, in particular a number field. So that's still nothing completely original about that. Of course, we're talking about polynomials, say, over the rationals, and if you take the field of fractions, these are just rational functions. So it's a very well studied thing. But I'm going to take the point of view of just looking at some arithmetic properties, which are very analogous to what's happening over the integers. So in particular, quadratic reciprocity. So let me just do kind of a strange notation. So let me let P and Q be polynomials. And I'll assume that P is a prime, so that means a monic irreducible. And I'll use a notation like a Legendre symbol. So Q over P. Now this thing is not a character. It's just a convenient notation. So you can relate it to the classical case. But this just means that Q is a square mod P, of course. So Q is a square mod P. Now, what does this mean? If suppose K is the rational numbers, then what this means is that when you take a zero of P is a polynomial, you're looking at a number field extension of Q, and you're asking if you evaluate this polynomial Q, say at the zero, is that a square in this field? That's really what this means. So the residue field is infinite. It's a number field. So you're not doing arithmetic modulo P as you usually think about it. You're doing arithmetic in a number field. So that makes it a lot harder, actually. Now, if K is finite, then it's a nice theorem of, I guess it goes to Artin, that you do have quadratic reciprocity. So you have Q over P is 1, if and only if P star over Q is 1. So instead of taking their product or something like this, because in that case, it really is a character, but I'll just write it this way. And this P star is, in the classical case, it would depend on whether P is congruent to 1 or 3 mod 4. But here it depends on the degree, the parity of the degree. So I'll write the degree as absolute value of P. Okay, so that's a very nice little theorem. I guess it's due to Artin. You can find a proof, and it generalizes to nth power residues very, very easily. It's actually not a very hard theorem. There's a nice book by Rosen on function fields, and he does this right away in the very beginning. Now, for infinite K, this can't be expected to always be true. So if K is infinite, like a number field, this isn't always true in multiple ways. So let me say what one of the goals of my talk is. So I'll say K is a number field. And I'll let Q be a fixed prime, Well, yeah, here we're assuming P and Q are primes. P not equal to Q primes. So Q is going to be a prime now. And I'm going to assume it's odd degree. Now, this is a funny thing because when you get into this, you find out that the parity of the polynomial, when you start taking residues modulo the polynomial, has a huge effect. So when Q has odd degree, things are much simpler. So I'm gonna stick to that case in this talk. So think of it as a fixed odd degree prime. And I want to characterize when is it true that you do have sort of a partial quadratic reciprocity? When is it true that Q over P being 1, so Q being a quadratic residue mod P, that this implies P star over Q is 1. So P star is a quadratic residue mod Q. So I'm not saying if and only if it's a one direction thing, but the hard part of this, or the content is, this has to be true for all primes, P not equal to Q. Okay, so I want to figure out a condition on Q where this will be true. And just to convince you that it's not always true, even when K is Q, which is always the case I think about, I guess, it's not all P or not all Q work. So here's a nice example to get you guessing where I'm going with this probably. So let's take this guy. Q is equal to T cubed minus 4. And take, so that's an odd degree guy, and it's a prime. So, and let's take P is equal to T minus 2, degree 1 guy. Then Q is congruent to 4 mod T minus 2. So a linear congruence. You're just looking at things in Q. So it's pretty easy to check this. But anyway, so what is it? So T cubed minus 4 minus 4. This everybody can check. When you know you're getting old when you have to do use Mathematica to check this. But anyway, so that's true. It's a square. On the other hand, 2 minus T minus, so that's P star because the degree is odd. So 2 minus T is not a square. Mod T cubed minus 4. And how do you see this? Well, one of the nice things about working in the function field like this is you can set the value of the variable equal to something and check what's happening in the field K. So here you just set T equal to 3 and check that if this were a square, this would certainly have to be true over Q or over Z, and it's not because minus 1, this is the real Legendre symbol, is not a square mod 23. Okay, so that one's, it's not true for every Q. On the other hand, if you just change Q a little bit, it is true. And I'm not going to actually be able to give an elementary proof of this. It'll follow from the theorem that I state. But if you just change the minus to a plus, it actually is true for this guy. So this does work. Okay, and maybe some of you are figuring out where I'm going with this by looking at those kind of familiar looking cubics, but we'll see what happens. Okay, now, where did this come from? Well, I was actually reading Gauss again, believe it or not. I tell people I make progress by moving backwards, and I keep going farther and farther back. I mean, I started with contemporary guys, Henrik Ivanits, Peter Sarnak, and I started going backwards. I went to Ramanujan, and I went to Littlewood, and I went to what else? And then recently I've been going really far back. So Cayley and now Gauss. And this is probably where it stops. Because I mean actually Euler. So
there's still Euler, yeah.
Because I was reading Weil, and Weil they studied these people and got lots of inspiration. So anyway, that's what I did. So I started looking at Gauss again, and his second proof of quadratic reciprocity is pretty interesting. It's in the Disquisitiones. And the reason I was interested in it is because he uses binary quadratic forms and genus theory. This is the inspiration. And okay, so I'm going to give a condition for this partial reciprocity to hold in terms of binary quadratic forms, but they're going to have coefficients in the polynomial ring. So I have to set up a little notation. Now, this is kind of a weird notation, but it's actually helpful. So if I have a polynomial, I'm going to say it's positive. Okay, it looks a little bit weird, but it turns out to be the right thing. If the leading coefficient, not of n itself, but of this n star. So if plus or minus n, its leading coefficient is supposed to be a square in the field. So that's what I'll mean by positive. Of course, if k is like, the Gaussian numbers, then it has nothing to do with actual positivity, but it actually does have some effects because if the discriminant of my form is going to be negative, so negative means, of course, so means minus n is positive. Then the forms are going to be very similar to positive definite binary forms. And their theory is a lot simpler. And these are the ones I'll be using. So, the notation will be familiar. Now, actually, for what I'm doing, it's actually better to use the Gauss notation, which everybody hates. So you have a 2 as a center guy because it's really a symmetric matrix. So associate to the symmetric matrix. So these A, B, C are polynomials. And I'll associate the quadratic form, usual way. But actually, this 2 is actually better for some things like this. Because if you don't use it, then you have to divide by 2 a lot of places. And I'll denote this by AB. So I'll denote this by ABC. So the B has always got this 2 when you make it a quadratic form. And the discriminant in this case is B squared minus AC. So there's no 4 there. This is actually kind of handy because if you're doing congruences, the 4 is a pain. So here, there's no reason to even worry about it because it's a unit in the ring. Everything in K is a unit. K star is a unit. So there's no reason to do this. Actually, I wrote a paper with Henrik and Friedlander years ago. We were studying the distribution of quadratic residues, and we did this for that very reason. So we used Gaussian quadratic forms, much to some people's dismay. But anyway, that was why. So how do you change variables? Well, sort of the obvious way. So we use SL2, the ring. You let it act in the obvious way. So Q/M is, so I'm not distinguishing between the matrix and the form. So you just have to go between them. That tells you how you change variables. Now here's why I'm going to suppose that D is negative in my weird notation. So that means that minus D, the leading coefficient of minus D is a square. And in fact, I'm going to assume it's monic. So 1 is a square. And I'm going to assume that the degree is odd. Well, here I don't actually need to assume that. So let me back up on that. Not assume that yet. And the other thing I'm going to assume is that A is positive, just like in the case of positive definite quadratic forms. And that's the condition you actually want. So I'm going to impose that condition on the form. And in the usual case, it just means the form is positive definite. But here, what happens is when you change variables, it retains this property. So the set of quadratic forms that have this condition is actually preserved under the change of variables. And that's not completely obvious, but that makes it very handy because every form that you deal with has this property that the leading coefficient of the A is a square. By the way, in working with this, I had tremendous headaches because the usual over the integers, the units are plus or minus 1, but here the units are k star, and they enter into the arithmetic in this serious way. And you have to either use them or remove them. You can't just, so anyway, it was just a pain. And so this turned out to be the correct thing to look at, for at least for what I'm doing. I also want to assume it's square free. So it's like a discriminant. Okay, and so just I'll let QD be the set of all these guys. And there is a principle that it's not an empty set because you always have the principal guy in here. No surprise. And as I said, it splits into classes. So this set splits under this equivalence. Usual type of thing. And I'll denote the classes, the set of classes. CD. Okay, so finally, here's the setup, and so I'll state the theorem, or theorem 1. So again, K is a number field, and Q is fixed prime, odd degree. Then this quadratic reciprocity relation holds. So I'll say it this way. This holds if and only if, I haven't said what it is, but if and only if the number of classes is finite. So the class number is finite. And what is the statement? Well, it's what I did before. So it's Q over P is 1 implies P star over Q is 1 for all P. Not equal to Q. Odd or even, doesn't matter. So this quadratic reciprocity relation holds if and only if the class group, or the group of quadratic forms is finite. Now, over a number field, this may or may not be true. Over a finite field, it's always true. So when it's finite, it's actually pretty easy. So in following the Gauss proof, that's really kind of where I started. Well, first of all, I'll just run through the ideas and show you where it's kind of interesting. So the first thing that, this is one of the motivations, I think, for Gauss to invent the group of, the class group. So this is a group under composition. And, you're already starting to think, well, why don't you just deal with quadratic extensions? And yeah, you can, but for some reason, for some things, it's actually, at least for me anyway, it's a little bit easier to work with the quadratic forms. And the composition here is not very hard. It's what happened. Gauss's definition is pretty involved, but Dedekind found a simple way to do it, and that goes through very smoothly in this setting. It actually works over any kind of Euclidean domain, even a PID. You can make the Dedekind definition of composition work really well. It's abelian. And what else do I want to say? I'll mention this a little bit more about this, but this is kind of the starting point. And you need this in order to apply this to quadratic reciprocity. So what's the next idea? Well, what Gauss did after he defined this group, first of all, it's finite in the case of Z, and this is crucial. Okay, so it's a finite group, and that's a theorem. It's a reduction. It's a proof by reduction. Everybody knows this. Here it may not be, but what Gauss had to do is he had to count the elements of order 2. And again, here it's still finite. So the way he did this is he looked at the forms that when you compose them with themselves give you the identity form, and they look like this. So they just have a 0 in the as the B. And you can pretty easily see that when you do composition of this with itself, you get the identity. But so this means that minus AC is D. So it's decompositions of D into a product of two different polynomials. And so you had to count these guys. If D is square free, he worked it more generally, but if D is square free, then these guys will be prime to each other. So it's a pretty easy thing to count the number of such forms. But the tricky part is when are their classes equal? So you have to count the number of classes of order 2 in terms of these guys. He called these guys ANSIPs, or ambiguous forms. That's what these guys are, versus ambiguous classes, which are the classes of order 2. Now, in the Gauss case, it's not tremendously hard, but it's not that easy either. And one of the problems is that these are not the only that these guys here. These guys here are not the only ambiguous forms. You can have guys where the centered guy is not 0, and the cause of the problem is the existence of 2 as a prime, as usual, right? God should not have made 2 a prime. But anyway, that's the cause of the problem. But anyway, he's able to count them in terms of the number of factorizations of D. And then he defined genus characters, which are quadratic characters.
Sorry, could I ask a question about this theorem?
Yeah.
So what is the relationship between Q and D?
Oh, shoot. You're right. I'm sorry. Q. They're equal. Thank you. Thank you, Ethan.
Okay.
Yeah.
Yes.
It wouldn't make sense otherwise, sure. Thank you. Okay, so we can define genus characters, or he did. And these are characters on the class group of order 2. They're all the characters of order 2. But to get quadratic reciprocity, really all he needed was the count of elements of order 2, the fact that the class number is finite, and then the fact that a genus character on a square is trivial. That's really that's what you need to get the quadratic reciprocity. So, and that last part's just obvious, right? So I won't write these things down again, but it's almost easy once you have the setup and you count the number of elements of order 2. Now, for me, for my theorem, it's part of it is very similar. So the if part, that if the class group is finite, then you have this quadratic reciprocity relation, is basically the same. It's I just have to define genus characters, and that part is very similar. And in my case, counting the elements of order 2 is actually easier because you don't have 2 as a prime. So it's really just a number of decompositions of D into a product of two relatively prime polynomials. So the if part, let me just say it that way, the if part is similar to Gauss. Now, Gauss went on and proved kind of one of the highlights of his book is to characterize the elements that are of order 2. I'm sorry, to characterize the elements that are squares in terms of the genus characters. So the genus characters are defined, they're locally defined. So he proved that the squares are exactly the elements that are killed by all the genus characters. And it's a local to global statement, really, because the genus characters are locally defined, and being a square is actually turns out to be a global statement because it's related to rational equivalence. But anyway, that's what he called. I don't know what he called it, but I think it was like he heaped a lot of praise on his own results sometimes, and that was one that he heaped a lot of praise on. But people will call this the principal genus theorem. So what I want to say is that the only if part of my theorem is quite a bit harder. And I have to use a few new ingredients. So it's going to use the analog of Gauss's principal genus theorem. If you're used to using algebraic number theory, then you have to translate this into that language, which of course you can do. But for what I'm doing, it's actually better to stick with the quadratic forms. So what does this say again? So this says that if you take the squares, then these are the classes that are killed by all the genus characters. And I haven't defined these yet. Okay, but let me say something again about the classical proof of this. So that what Gauss did is he, well, first of all, the genus characters are basically quadratic characters where the modulus is a prime dividing the discriminant. And the value of the character is a value, is an integer prime to the discriminant or prime to that prime represented by the quadratic form. But in terms of quadratic fields, it's just the usual kind of Hecke character of order 2, or genus character. But the way Gauss proved this is he used ternary quadratic forms. I think he actually developed the whole theory for this reason. And he does a reduction theory of ternary quadratic forms, namely this one. That's a ternary quadratic form in A, B, and C. And he developed reduction theory and showed that the ternary forms that you need to prove this theorem reduce to this guy, basically, and that's where the theorem comes from. But in the reduction theory, it heavily uses that. Here's the property that's being used, ultimately, that there are finitely many integers of bounded norm. We all like that property, right? There are finitely many integers of bounded norm. All these reduction theories are really use this in one form or another, because they put you have a norm, and then you somehow get whatever you're reducing to have a norm which is bounded. So the number of integers always comes into this. Now, for what I'm doing, that's not true, because the number of polynomials with a bounded degree is infinite if the field is infinite. So that's a big difficulty. It's because the residue field is infinite for me. So if I'm going to do something like the principal genus theorem, I have to do something else. So I can't use reduction theory. The other, you could try to do it perhaps using a different norm, using height, but that doesn't fit in well with the other part of the thing I'm doing. So this was an interesting difficulty. The other proofs of this, for example, Dirichlet gave a proof in his book on Gauss, basically, which reduces it to Legend's theorem on ternary forms, which is also, most proofs of that are done by some sort of reduction theory, some sort of counting of integers. And the other proof, to Dirichlet and Kronecker uses the class number formula. So it uses L functions. It's a nice proof, right? But the L functions, their definition uses that there's finitely many integers of a bounded norm. So that always seems to come into play in these proofs. So I had to do something else. So the way I did this is I used the idea that genera are the same thing as rational equivalence classes. And this is possible to prove here. And the reason is there's a very interesting theorem of Milnor. So I apply a theorem of Milnor. Now, when you go to rational equivalence, quadratic forms over a field are a lot simpler, and they have a lot more structure than quadratic forms over a ring, like the ring of integers or polynomial ring. But over a field, they have a lot of structure. You can always diagonalize them. And there was a beautiful theory of Witt, who turned the set basically of quadratic forms over a field into a ring under direct sum and tensor products, where you start pasting together quadratic forms. And so Milnor, and actually Harder and other people were involved, but they characterized the Witt ring of a function field over, so let me say this. So the Witt ring, you define this up for any field actually, but the field of interest here is the field of rational functions. He was able to characterize this locally, which characterizes it. It's a isomorphism. It locally. So, well, locally here is actually not pi-adically. I mean, this is another thing. So when you have a prime in this setting that I'm talking about, it's a irreducible polynomial. So you can do, p-adic theory, but then you're talking about powers of prime, modulo powers of prime, and you can do it, but it's a little bit harder to work with than the residue class fields. So, and in fact, his theorem is in terms of the residue class fields. So let me just call them this FP. So what is this? This is the K of T, this ring modulo P. So the usual kind of field. You can think of this as a number field. But anyway, so it's in terms of this for all P. For all P, right? So that's a huge set. But he doesn't use any kind of finiteness property of polynomials of bounded degree. And so what is actually it's pretty straightforward once you set it up, because I'm only dealing with binary quadratic forms. This Witt ring deals with all quadratic forms of all sizes. So things are simpler when you just have binary quadratic forms. So I was able to apply this theorem to show that genera are the same thing as rational classes. Well, I still haven't defined genera, so let me do this. Well, actually, let me put it off. Okay, I'll come back to this. I don't mean to give the whole proof right now. Now the other part that's harder in the only if part. So the other part of the only. So you need to know this thing, which seems obvious at first, but you need to know that if CD is infinite, if this class group is infinite, I need to know that there's a class in it that's not a square. Okay, well, okay, so here's where the big gun comes in, because this is true if you know it's finitely generated. And that's the second part of the proof. And so this is the Mordell-Weil theorem, since we're working over a number field. Okay, now it's not completely obvious how this applies. Well, so what you do is you show that this class group, the way I've defined it very carefully, I mean, plus or minuses, all this stuff comes into play, but this is isomorphic to the divisor class group or Jacobian. Of the hyperelliptic curve, a hyperelliptic curve defined or determined by, you can guess, s squared is equal to d of t. So I'm assuming this d is square free and monic, and it's defined over this number field. So we have this hyperelliptic curve, and you have to, in general, the degree of d is odd. I'm assuming that. And this is really where it comes in, because if the degree of d is even, it changes. It's really, there's actually a kind of a beautiful analogy between the parity of d and whether you're talking about real in quotes, quadratic extensions or imaginary quadratic extensions. So I'm looking really at imaginary quadratic extensions, and there's only one point at infinity that you need to add to these affine points to make this into a nice curve. And then once you do that, so the way you really do it is you do look at the function field. But then you can prove that the Jacobian is isomorphic to the group that I've defined. Now, this is not completely original. I learned about this from, it actually goes back to Jacobi. He did not do this, but he used polynomials. Now, the polynomials are the polynomials in A, B, and C in the quadratic form. Jacobi actually used those polynomials to deal with a hyperelliptic curve Jacobian, his Jacobian, right? But then Mumford, in his Tata lectures, used that. He really brought it out to show that the Jacobian is actually can be made into a variety, into an abelian variety. He used this polynomial interpretation. And then Cantor, David Cantor, in kind of a famous paper amongst people who do cryptography, actually showed that if you do, you can define the addition in the Jacobian using something that looks like composition of quadratic forms. In fact, it is. So these guys did this, but what they never did actually is to show that exactly there's an isomorphism between the class group of quadratic forms and the Jacobian. As far as I know, no one's done this. And maybe they have, but it's kind of implicit in their work. It's not really that surprising that it exists, but I needed it to be very precise. Okay, so if you believe this, then and you apply Mordell-Weil, then you have this property that you have non-squares if it's infinite, and then you can play around with this. So the final ingredient, you need to make primes that are in this non-square class, and the way you do that is you apply the Hilbert irreducibility. Now, one of the simpler things about these guys, these quadratic forms, is that it's easy to make primes that they represent because you have this variable. So the Hilbert irreducibility, vaguely speaking, says if you have a polynomial that's irreducible in, say, two variables, that's irreducible over a number field as a polynomial in two variables, then you can specialize one of the variables in infinitely many ways and get something irreducible. So you can use that pretty directly with these quadratic forms in terms of the variable, say, x and y, and make it represent irreducibles. So unlike over Z, that's sort of a hard theorem, right? To show that quadratic forms represent primes. Here it's pretty easy. So that's the other ingredient. Okay, now you haven't seen really what's going on in the proof. I've used lots of words. And I guess given my, is it really that? Wow. Okay, so let me, that's okay. So anyway, this explains those examples that I started off the talk with, because these are elliptic curves. So this applies in the case of elliptic curves. So the first one, this has rank 1. It's infinite. So that's why it explains why it doesn't always hold. In the second one, the rank is 0. So if you believe my theorem, then it's true. Okay, now I can't help but state the theorem 2, which I really like. Now, in the classical case, Gauss didn't really use his principal genus theorem directly as an application to quadratic reciprocity, but this was done after him. I think he probably knew this, some aspect of this, but this was done after him. So he proved, he evaluated the number of elements in the class group of order 2. But the question about higher order, of course, was very interesting. And so you can use the principal genus theorem to count elements. A better way to put it is you look at the class group and you put it into its canonical form as a product of prime power cyclic groups. And you can count the number of these cyclic groups whose order is divisible by 4 using the principal genus theorem. So this will not be that unfamiliar. I mean, lots of words here, but this was done by Red Eye, I'm not sure how to pronounce his name, and Reichert. So they proved this. So if you take D as a fundamental discriminant, in the usual sense, and you look at its decompositions, where these guys are relatively prime, and they are also fundamental. Now, counting these decompositions is the same as counting, elements of order 2. So these are prime, this is a nice way to put that. But what they did is they said, well, if you put an extra quadratic reciprocity condition on these guys, you can count these, the number of factors, or the number of invariants divisible by 4. And so the condition is that you take one of these factors and you take all the primes dividing the other factor. This has to be 1. And the reverse also has to be true. Then the number of these decompositions will tell you the number of these cyclic factors divisible by 4. So it's really beautiful. So it's a condition you're putting on the decompositions. And in fact, their proof used quadratic, they translated everything into class field theory. But what's going on is they're counting elements of order 2 that are squares. And so you can use genus characters to do this. So the elements of order 2 that are killed by the genus characters. And that turns out to be exactly this condition, or these conditions on D1 and D2. So, but you need the principal genus theorem to prove this. So that's really a nice application of the classical principal genus theorem. So I was able to give an analog of that theorem too. I don't know if this is known in any form. I wouldn't be surprised, but so again, K is a number field. And D is square free. And odd free. And I'll let T be the torsion group of the Jacobian, which I talked about a second ago. I'm being a little bit vague here, so S squared minus D of T. And I'll let E4 be the number of cyclic factors. Prime power of order 2 to the n, where n is bigger than or equal to 2 in the decomposition. Then you have the exact analogous result. So 2 to the E4, then 2 to the E4 is the number of decompositions. Of D is equal to D1, D2. These are polynomials now, but these guys are monic. If D is odd, then one of them's odd and one of them's even. So I'll say that D2 is odd. I'm sorry, so D2 is odd. Such that D1 over P is 1 for all P dividing with D2. And D2 minus D2. D2 is odd, so that's D2 star over P. So it's just the direct analog. Okay, now the number of guys of order 2 is exactly like in the classical case, and this is really well known, that you get the elements of order 2 in the Jacobian by factorizing D, the number of factors of D. Now, the way to think about this, I should have said this, the polynomials that are occurring, like A, so you have B squared minus AC. Let me write this down. This is not obvious. So B squared minus AC, this is D. Okay, so if you have zeros of A, they're going to make D be a square. That's all that's happening. Zeros of A make D be a square. So if you have a polynomial, its zeros will define a divisor. And the x coordinates of the divisor. And the values of B at those zeros will give you the y coordinates. That's the idea. It's very simple, but it's quite nice because you're getting points on the Jacobian using polynomials. You don't have to go to the algebraic closure to get these points. You can just identify them, the divisors, with the polynomials. As I said, this is not my idea. It really goes back to Jacobi, Mumford, and Cantor. But it's well known that the divisors of D give you the points of order 2 in the Jacobian, these divisors of order 2. But the ones of order 4, it's probably known. I mean, there's so much work being done that's been done on these Jacobians. This probably follows from some theorem. But what I like about it is it's so elegant. It's exactly analogous to what's happening over the quadratic field. So you can apply it. You can apply it to elliptic curve and get these well-known results about points of order 4. But when you go to higher genus, it's kind of interesting. You can check it out. It's quite fun. Okay, so I've got to say more about what's happening with the theory. So the theory goes through very much like the classical theory. So this is incredibly brief sketch. So you have reduction theory. You do have reduction theory. It just doesn't give you finitely many classes. But it's like in the case of positive definite binary forms. For example, you have a unique, it's even nicer than the positive definite case. You have a unique representative form of discriminant D, where the degree of B is less than the degree of A, is less than half the degree of D. Well, D is odd, so that's why you get this strictly less, and where A star is monic. So these quadratic forms have a unique reduced representative, which is nice. You don't have any kind of, fussing around with fixed points or anything like this, but you actually have unique reduced guys. Now, in terms of the Jacobian, this is kind of familiar because what this corresponds to is it corresponds to a divisor given to you by the Riemann-Roch theorem, which is actually unique in this case, in the odd case. So it exactly corresponds to that. And that's what makes the isomorphism pretty easy, actually. So you do have reduction theory. You have composition. I'm not going to have time to go through that, but a la Dedekind. So you have his approach works almost exactly the same, just a few little things. You have ambiguous forms, ambiguous classes. You can count them, and it's just like counting factorizations of D. But the new part, the part I kind of emphasized is the genus theory is, and the principal genus theorem is a little bit trickier. But there's a very nice thing. It's called a Steinberg symbol. Used a lot by Milner and Tate and other people, which is kind of a Hilbert symbol. And it works very well with these rings of polynomials. It's very simple, actually. So if you let, again, this FP is this field, the residue field. And so I can define this Hilbert type symbol in sort of a very, very elegant way. So you take the valuation of P of A and the valuation at P of B. So A and B are, these can actually be in the field. So these are in KT star. And then you take A to the valuation of P, B, and B to the valuation of P at A. And you think of this as being in FP, FP star mod FP star squared. So you only consider it up to squares, just like the Hilbert symbol. I mean, usually the Hilbert symbol, you say it's plus or minus 1, but you can also think of it as living in the integers mod P, and either plus modulo of the squares mod P, which is, you can identify those guys with plus or minus 1. So it's better to do it this way because these FP is a number field. So you're looking at this rather complicated group of things in a number field modulo their squares. But that's where these guys naturally want to live. And I should say this. So A is P to the VPA. U, where P doesn't divide U. We have unique factorization. And you do one at infinity, similarly using the leading terms. So this is where that comes into play. Yeah, so I won't bother to define this. You have a product formula. Now this is I learned about all this stuff in a book by Milner on K-theory. So he used this a lot, but mostly over the integers, but it also applies over these function fields. And you have a product formula, and that's actually the same thing as Weil reciprocity over this simple function field, the product form. You can kind of imagine that because you're counting, when you have this prime, you think of it as it's zeros, it's giving you zeros of a polynomial. But anyway, you define the genus character, and here I'm going to have to stop using this guy. So you still have this property that you can represent polynomials that are prime to D or prime to P. Just like Gauss, it's really an important thing that with Gauss. And then you can use this Hilbert symbol to define the genus character. So you would say chi P of Q. It's kind of the obvious thing. So you say N D P. So it's not really a character. I mean, it's got its values in this quotient of FP mod FP squared. But then you can use this to define the genera. And the content of the theorem is that the genera are the same thing as rational equivalence classes. This is true over Z. And it's also true here. And this is where I use this theorem of Milnor I talked about. So once you have that, then this is where I'll end. So you see the relation. If I have something which is rationally equivalent to the trivial quadratic form or the principal quadratic form, I will have something like this. I'll have Q of Y over X over Z and Y over Z is equal to 1. Now, factor out the Z. So you get Q. Now, the X and Y and Z are polynomials. So rational equivalence can be manipulated into saying that you represent a square. And representing a square means you're in the principal genus. So this is not a coherent argument, but I'm just throwing out the idea. So if you are able to get rational equivalence, you can get your hands on the relationship between the genera and the principal genus. I mean, the genera and being a square in the class group. So that's really where that comes from. And then once you have that, you can proceed fairly easily to get these theorems. Yeah, so yeah, I think I'll stop there. Well, yeah, there's something that I mentioned is that when, the degree of Q being odd or degree of D being odd shows up in several places. It shows up in setting up what should be the quadratic forms, because I don't think my theorem 1 is ever true. Well, it's true, but I think that the class group is always infinite if the degree of D is even. So you have to do something else to get a nice theorem out of it. And it also shows up in the Jacobian. And this is something that's bothered other people as well, who tried to make We's original proof of Mordel's theorem. His original proof uses just algebraic number theory. So it uses what are very similar to these genus characters. And he proves that essentially that the images of the genus characters form a finite group. That's what's really behind the Mordell-Weil theorem, is that the images of the genus characters give you a finite group. And in the odd case, it goes through fairly easily. It's not easy. Here's my moral. Doing arithmetic in the divisors is hard. Doing arithmetic with quadratic forms is easier. So these guys have always been working with arithmetic in the divisor class group. And you run into problems, two infinities causes problems, believe it or not. And the same problem is going to show up here as well when you have even D. But the arithmetic is actually very similar in both cases. But I think it could be useful to try to do things with further things with the Jacobian using this kind of language. As I said, Cantor pointed this out, and the people who use Jacobians over finite fields use this all the time. They use this observation of Cantor. So he was really finding an algorithm for doing arithmetic on divisors. But he never actually left the divisors, and nobody ever leaves the divisors. And I'm saying go to the quadratic forms And and if you want, go to the quadratic field extension. And a lot of the arithmetic there is a lot easier, actually. Okay, so I'll stop.
Okay, thank you very much for the nice talk. You can also clap in the chat. So are there any questions for Bill? You can just unmute yourself.
I see a bunch of hands. Oh, I see them. They're clapping.
Yeah.
I'm out of it. I'm an old guy. This is all bizarre for me. I'm not used to it.
So maybe you have a question. So this.
There's chats. I should be able to see that.
Uh,
No, there's nothing, right?